Why, sir?
I don't know. It said to start streaming, you will be removed, but it didn't happen.
Okay, I'll leave now and I'll join,
No,
sir.
no, no. You can stay.
Okay, sir.
Now, I don't think any issues. Yeah, so streaming has started. I have pasted the YouTube link in the chat, and also I have pasted it in the calendar. Okay. All right. So, lots of things to discuss. Before we start, I will give you a gist of what we are going to do today. So, today we are going to discuss the most important topic for the exam quiz 2. Also, this is the starting point for the concept integration. So, this is also really important as a concept too. Okay, which is Riemann integrals, Riemann sums. Okay, so that we will start with that and then discuss what a definite integral is, how a definite integral is defined from the Riemann integral, Riemann sums. And then from definite integral, we will drop the limits and then define what is integration mean. Okay, so it's not integration came first, then definite integral, then Riemann sums. It's Riemann sums has come first, then the definite integral, then the integration has came into the picture. So chronologically, Riemann sums are the starting point, and you should really understand the idea of Riemann sum, and you should really appreciate at that time Riemann has come up with this kind of method. So what exactly this Riemann sums capture, right? So the main idea of Riemann sums is to approximate the area under a curve by small vertical rectangles. So what do I mean by vertical rectangles? Vertical rectangles are rectangles where the length is very small, but the height is very large. So something like this. Okay. And small, I mean small, I represent the length. So the length is very, very small. Area is also very small. Okay. So we are going to use this vertical rectangles and we know how to compute area of a rectangle. So that we know. We are going to use the area of a rectangle to approximate the area under a curve like this. So for example, you have f of x, you plotted f of x, and you are interested to compute the area under this f of x, between the intervals x is equals to a to x is equals to b. So that means I need this region R. But this region R, I don't have any formula that I can directly use and get the area. So what can I do? I will try to construct some rectangles and such that the area of those rectangles are approximately equal to this particular region R. And how do I start? I'll start like this. So what do I do? The very first step, what I will do is, I have this interval AB, right? So I have to start from A and end at B. So what I will do is, I will break this interval into smaller intervals by bringing up new points between AB. So like this. So I will choose x1, I will choose x2, I will choose x3, x4, and so on, xk minus 1, xk, and so on, xn minus 1. So I will introduce these points. Okay. And here what we will do is we will equally divide every interval. So the length of this and the length of this and the length of the next interval all are same. So the total length comes out to be b minus a, because b from a to b the length is b minus a. So this interval AB is of length b minus a, and I will divide that interval, the whole interval, into n subintervals, n equal intervals. So when I say equal intervals, so the total is b minus a, and I have to have same length in n intervals. So each interval will be b minus a by n, right? So delta here represent the subinterval length, the width of each interval. So this width xk minus 1 should be b minus a divided by n. So if you are dividing the whole a to b into two intervals, okay, so two intervals is like one interval should be b minus a by 2, another one interval should be b minus a by 2. If you are dividing the interval a b into three intervals, so b minus a by 3 will be the first interval, and the second interval will be b minus a by 3 of length, and the third interval will be b minus a by 3. So like this, if you are dividing the interval into n intervals, n is like any number, right? So this n can be 10, 20, 30, 40, 50, whatever. But as you increase n, what will happen? Length of each interval will reduce. So if I take more and more subintervals, each subinterval length will reduce because n is in the denominator, right? So if you are taking too many components, each component length will be smaller, smaller and smaller. Okay, so what we did is we have divided the whole big interval AB into smaller intervals like this, and we have drawn these straight lines. So you draw or don't draw, but it will just give you an idea that we, instead of taking AB as a whole, now we are working it as some n equal intervals, sub intervals. Okay. So I hope this idea is clear. And you can also find x1, x2 in terms of A and B. Right? How can I do that? I know this is delta. Right? And a delta is B minus A by N. Right? So if I have to get x1, x1 is basically A plus delta. And A plus delta is B minus A by N. So this will be NA plus B minus A by N. That is N minus 1 A plus B by N. Right? So this is x1. So like this, if I want to find x2, x2 is basically 2 delta far from A. Right? So x2 will be A plus 2 delta. So you substitute delta as B minus A by N. You will get x2 in terms of A, B and N. So like this x3. So x3 will be A plus 3 delta. So like this xk will be A plus k delta. Right? So you can find all the points in terms of A, B and N. Because A, B and N are known to us. So you know B, you know A, you know N. How many subintervals you are making? Whether it is 3 or 5 or 10 is what N values. Okay, so once you have, you will get these points. So what we have to do is we have to find these points first. First step will is to find the points x1, x2 to xn minus 1. Okay, and what we do next? So the second step should be, once you find this x1 to xn minus 1, now what you have to do is you have to choose. Yes, Sudhanshu.
Sir, I have a small doubt. Sir,
Hmm.
if we are finding delta, that is the change, then why we are dividing by answer, BA upon N? Like it should be only B minus A, I think.
No, delta here is not the whole interval. Delta here is the length of each subinterval. So smaller interval. So what this length is what delta is.
Oh,
Okay.
so okay, okay.
So you see, you have n such intervals, and sum of n such intervals should be b minus a. So the total length,
Okay, sir.
right?
Okay.
So n times the delta should be b minus a. Now you bring n to the right hand side, it will come in the denominator.
Okay, sir. Got it.
You got it, no? Yeah. Right? So delta, 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 delta. So like this, there will be n deltas. N delta should be b minus a. Okay. So after choosing x1 to xn minus 1, then what we have to choose is, again, we have to choose another point, which are C case in each subinterval. So if this is the first subinterval, A to x1, so you have to choose some point, some arbitrary point C1. So it may not be the midpoint. It can be any point between a to x1. Okay. So this C1 is chosen in this particular interval. Like this, C2 is chosen between the second interval. Likewise, Ck will be chosen in this kth interval and Cn will be chosen in the nth subinterval. So we'll have C1 to Cn, right? And why are we going to choose these points? Because we have to construct rectangles. So what is the main idea of choosing this Ck's? Once you choose Ck, once you choose Ck, so you choose f of Ck as the height of that particular kth rectangle. So how do I construct? So these subinterval lengths will act as the lengths of each rectangle. We have to get the height also, no, to construct a rectangle. So for height, what we are going to do is you choose some arbitrary point in each interval. Arbitrary point Ck in each interval. And after choosing Ck, you just compute f of Ck. Okay. So, so Ck and f of Ck is here. Now f of Ck will be the height of your rectangle. Now construct a rectangle with length delta and height f of Ck. So that will give you the kth rectangle. That will form you the kth rectangle. So you can start from first. So you choose C1 and after choosing C1, find f of C1. F of C1 will be the height. So this will be f of C1, right? And this is delta. And you have the first rectangle. And move to the next interval. Next interval, you have the length, delta. And what is the height of this? You have to choose a point C2. After choosing a point C2, you compute f of C2. And that will act as your height of this rectangle and you form this rectangle. So likewise, we have n subintervals. So you will form n rectangles. Okay. Now, once you get n rectangles, you have to compute each rectangle area, right? So what is the area of each rectangle? So if you see here, Ck, kth rectangle, you have the delta as the length and the height will be f of Ck. So observe that Ck is not the midpoint. So it may not be the midpoint. It is any arbitrary point. If I choose Ck here, f of height will be this much. If I choose Ck here, then the rectangle would have been like this. So height will be increasing, would have increased. Okay. So the rectangle area depends on the point you choose, right? So the Ck affects the area of the kth rectangle. Similarly, all Ck's that you choose will affect the areas of each and every rectangle, right? So here, if I choose Ck like this, then the area of the kth rectangle will be f of Ck. So this height times this delta. And we know what delta is. What is delta? F of Ck into delta is b minus a by n, right? So once you choose Ck, you know Ck. So once you know Ck, you know f of Ck. So this is known. And once you decide on how many rectangle subintervals you are doing, then n also known to us. Similarly, b and a are also known to us. So everything is known. Therefore, you can compute this area. So once you can compute the kth rectangle area, what do you have to do next? So once you have areas of each and every rectangle that you have, then you just have to sum up all the areas. So if you sum up all the areas, what will you get? So this is the area of the first rectangle, f of C1 times delta. This is the area of the second rectangle, like that. This will be the area of the nth rectangle. So if you sum everything up, you will have, in the shorter notation, you will have this summation k is equals to 1 to n f of Ck times delta. And this can be computed. This can be computed. The only catch is you have to decide on how many subintervals you are doing. which is n. You have to decide on n. And what points you are choosing, this C case. So this C case plays an important role. Okay, so that will affect the area. But once you compute this area, compute this sum, what we say is this is approximately the area of the region R. Okay, so just go back. What is our goal? Our goal is to compute or approximate this area. What we did, we have divided the whole AB into smaller intervals. And after dividing into smaller intervals, we have chosen some points in every interval, 1 point in every interval, which will decide our height of the rectangle. So once we constructed rectangles, so you'll have rectangles everywhere like this. You see, so all will be rectangles. So you'll have rectangles like this. So rectangles will fill up and you just have to add up all the rectangle areas. And we say approximate. So that will be approximate because you see here, you see this region is in the region R, but it is not computed when we compute area of the rectangles, sum of areas of the rectangles, right? So this will be leaved out. Whereas you see this one, this is outside region R, but we are still counting it when you compute the area of the rectangle, right? So like that. So sometimes some extra area will be computed. Sometimes an area that has to be computed will be leaved out. Okay, so therefore, this will not be the exact area, whereas this will be the approximate area. Okay. And yeah, so if you increase, so in order to get the exact, yeah, so that's why we are saying approximate area. So in order to get the exact, what should we do? So in order to minimize this blues and orange squares, what should we do is we have to reduce the lengths of each and every rectangle. Okay, so you have to reduce this delta. So how can I reduce this delta? By increasing the number of subintervals. So if I just consider subinterval as like this, now I will have rectangle like this, right? So smaller rectangles, you will have smaller difference. So the approximation will be better. So as delta goes to 0, so if I make this infinitesimally small, so what do I mean by infinitesimally small? So I choose A and I choose the very next point which I can choose. Okay, so the very next point, and I say that will be the length of the rectangle. Okay, so A plus delta, very small. And that I will form a very small rectangle. So it will be almost like a straight line, right? So like this. And I will do same for the next step. So I will choose infinitesimally small and small deltas, which will give me better and better approximation. So that is what Riemann said. So what he said is, you have this summation, which is okay, which I will denote it as RNXFAB. So you see, N should be known, A and B should be known. Okay, so this notation is N is the number of rectangles that you form. Okay, so which is nothing but saying N is the number of subintervals. Okay, so here X, this capital X, is the points that we choose. Okay, which are C1, C2, CK. Okay, and AB is the interval in which we are interested. Interval. Okay, so giving all these things to you, we can compute R and X of FAB. So how we can do that? We can do summation k is equals to 1 to n f of Ck into b minus a by n. This is the nth Riemann sum. Now, in order to make this approximation better, what we have to do is we have to reduce delta. So how I can reduce delta? If I increase n. Increasing n is nothing but you increase the number of subintervals. And you increase such that n goes to infinite. So you have to be really picking infinitely number of rectangles in order to get the best approximation. So what we are going to do, limit n tends to infinite, Rnx FAB. Okay, so you have to tend n to infinite. Then you will get the exact area. So here I have put equal to area of the region R. Okay, so once you compute this summation, you will get everything in terms of n. Right, so n, everything you will get in terms of n. And using the limits that you have learned, you have to tend n to infinite and see where this Rnx FAB is going. So if it is a bounded region, you will always get this limit value to be equals to some real number. If it is like infinite area, you are trying to find the area under this curve. So you have this and you are trying to find the area from 0 to some 5. So then this particular region is unbounded. So if you try to compute the Riemann sums and tend n to infinite, you will get infinite because area under this curve is infinite. This goes like anything, right? So this is not bounded. So you'll get infinite. Whereas if you just shift the interval, you say you are interested in this interval, 1 to some 7, then you will get bounded because 1 to 7 is just bounded region. You can get the area. Okay. So that is what main idea of Riemann sums. So what we are doing is to approximate the areas. And this is one technique to approximate the areas using the ideas of Riemann sums. Okay.
Sir,
Hmm.
how it is bonded when we take from 1 and not from 5?
No, I'm not saying not from 5. Initially, we are looking from 0 to 5. So after 0, it is unbounded. So that is why 0 to 5, we cannot find. Whereas from 1 to 7, we can find because 1 to 7 starts here and the area under this curve is from
Okay,
here to here.
under 1 to 7.
Under 1 to 7, it is bounded.
Okay.
Under 0 to 5, it is not bounded. Because after 0, it is like 1 by x. I took, this is 1 by x. Okay. So
Okay.
after 0, it will be like infinite. The value is very much infinite. So you will have infinite area. Okay. So you cannot
Okay.
use the ideas of Riemann sums to compute area under this curve.
Sir, between 0 and 1, we get 1 by x or something.
No, between 0 to 1 also, see, after 0, you have, this will never touch y-axis, right? So this will go like this to
Yes.
infinite. So if I am looking after 0, if I form a rectangle, that will be like infinite height rectangle,
Yes.
right? So therefore, the summation will go to infinite.
Okay, sir.
Okay. Yeah. So all I mean to say is the area that you are approximating should be bounded. Bounded in the sense, if I compute the area, that should lead me to a finite value, finite real value. Okay. It should not give me infinite. Okay.
Sir,
Hmm.
one question.
Hmm.
We are finding out the area under a curve because we are interested in the relationship, the product of what is plotted on the y-axis and the x-axis, right? Or
Uh, in
because
some sense, yes, but see, sometimes see area under the curve gives us much more some other information, right? So if you take for example velocity versus time. So what does area under the curve represent?
uh, VT, uh,
Uh, Acceleration in some sense.
V by acceleration will be velocity upon time, right?
Huh. So you sorry, distance versus time. If you plot
Right. DT.
and area under the curve, what will area under the curve give me?
Um, Again, it will be distance into time. One thing I can think of is like thinking energy, power, and energy. When you talk
Huh,
about
huh.
power, and then when you take the area under the curve for that instantaneous power, then
Hmm.
we get energy, which is
Right,
conserved.
right. So that is there, and also velocity versus time. Even velocity versus time, area under the curve gives me the distance that it covered.
Velocity. Okay.
Okay, because x prime of t is v of t, right? So distance covered divided
Right.
by
Right.
time
Right.
will
Right.
give you velocity.
Right.
So something like this. So area under the curve sometimes has significance, which is
Okay.
essential to compute.
Okay, sir.
Okay.
Sir, and one more question.
Hmm.
Here we know the function,
Hmm.
and we are talking about the area under the curve. Now,
Hmm.
suppose we have a plot with us, but we
Hmm.
don't know the function. So, is it possible to approximate the function? Uh,
Then it will be slightly difficult. Then we have to use the idea of unit squares, and we will try to use the very basic thing. Like we will try to fill the unit square number of unit squares, full unit squares,
okay,
and then approximate the area. Okay, so here the thing is we should know f of x,
okay,
right? So
okay,
yeah, all right. So as I was saying, the C case plays an important role in computing the areas. There are some special cases of choosing this CK. Okay, so take this kth interval again. So if you choose CK here, then the height is f of CK like this. Okay. The special cases of CK are, if you see, CK can be chosen anywhere between xk minus 1 to xk. Okay, so the special points are what happens when I choose the leftmost point as my CK, or what happens when I choose my rightmost point as CK, which is when CK is taken as xk minus 1, when CK is taken as xk, and there is one more thing, CK can also be taken as the midpoint, xk minus 1 and xk, right? So these are the three special cases. Anything else is not that special, right? So actually everything is random, but these are kind of special because the leftmost point is unique. You cannot have two or three different leftmost points. Same goes with rightmost point also. Same goes with midpoint. So midpoint is like a unique point. Anything else is like choosing this point or the very next point doesn't have that much significance. Everything is very near to xk minus 1. Okay, so there are some special names to these Riemann sums when I choose CK specially. So if I choose the CK as xk minus 1, the very leftmost point, and this should be consistent with any other interval also. So this is the kth interval I am showing you. Even for the first interval, second interval, third interval to nth interval, we have to choose all our CKs as the leftmost points of each and every interval. So if I choose CKs like that, then the sum which you are going to compute is called the left Riemann sum. So here left determines what is your CK points. So left determines that I have chosen CKs to be the leftmost points of each and every interval. Okay. If I choose CK as the midpoint, so midpoint will be, if I have 2 points like this, midpoint will always be that plus the 1 xk minus 1 plus xk divided by 2 will be the midpoint. So if I choose CK to be the midpoint, then the sum is called mid Riemann sum. If I choose ck to be the rightmost point, ck to be xk, then the sum is called right Riemann. Okay, so these are the three different sums. Even in exams also, we might ask you to compute the right Riemann sum. So what do I mean by right Riemann sum? So you have to choose all ck's to be the rightmost points of each and every interval. Right? So here, if I choose like this, my ck's will be x1, x2, and so on, xn minus 1 and b. So you have to start from x1 and you have to go till b, because those are, so k starts from 1 to n, right? So C1 will be your x1, C2 will be your x2, C3 will be your x3, and so on. And finally, Cn will be your xn, which is nothing but b here. Okay. If I choose the left Riemann sum, your C case will be, the first one will be x0, which is a, right? And then you have to choose x1, x2 to xn minus 1. So b will not be chosen because you are choosing the leftmost point. So your C1 will be x0, your C2 will be x1. So you have to subtract 1. Right? So finally your Cn will be xn minus 1. Okay, so these points you have to choose for left Riemann sum, these points you have to choose for right Riemann sum. And for the mid Riemann sum, you have to compute always. So you have to take x0 plus x1 by 2 will be your C1. x1 plus x2 by 2 will be your C2. So like that, finally even for Cn also it will be xn minus 1 plus xn divided by 2. That will be your C points. So once you have this, then you can compute. Right? So let's do an example. Let's say you have f of x to be 1 by x, be a function, but defined in the interval 1 to 5. Okay. And divide the interval 1 to 5 into, this is important, 4 regular parts, 4 regular intervals, parts, whatever. Okay. So you have to divide 1 to 5 into 4 subintervals. Okay. So here n is given to us. This is n. So n is given to be 4. Right. So first and foremost thing to do is draw a rough plot. Okay, how does this look? This looks something like this. And plot 1, this is 1, and this is 5. Okay. Now, we are interested to compute the left Riemann sum, right Riemann sum, mid Riemann sum in this region. So 1 to 5 region. Something like this, right? So this region. And the first thing that is given in the information itself is, you are going to divide this whole interval into 4 subintervals. So if I do 4 subintervals, this is how it looks. So this will be the first subinterval. This is second, this is third, and this is fourth. Now, what will be the points? What will be these points? X1, x2, x3? Anyone? So we know the delta, right? So delta is b minus a by n. So here b, a, everything is given to us. A is 1, b is 5, and n is 4.
2,
So
3,
the first
4, and 1.
2,
Sir,
3,
2, 3,
4.
4, 5.
4. Yeah.
Correct. So once you have 1, 2, 3, 4, 5, we have x1 to, sorry, x0 to xn. Now, in order to compute the left Riemann sum, how should I choose my C case? For the
1,
first
2, 3, and
rectangle, it should be 1, because I have to choose the leftmost point in the first interval. The second point is 2 for the second rectangle. For the third rectangle, I have to choose 3. For the fourth rectangle, I have to choose 4. I don't have to choose 5 anymore. So I have to choose 1. I have to compute f of 1 and construct a rectangle. I have to choose and compute f of 2 and construct this rectangle. I have to choose 3 for the third rectangle's height and construct the third rectangle. I have to choose 4 for the height of the fourth rectangle. So once you have these four, you just have to add up all four areas, right? Which is not accurate. As you can see from the graph itself, it will not be accurate. You will get more, but that is okay. So we'll say, since you have just divided it into four subintervals, your error will be higher, right? So as you increase, then your error will reduce. And I think this can be computed, right? So I'm not going to compute the whole thing, but the first rectangle area is simply f of 1 times 2 minus 1, which is 1, right? So this is 1. So the length of each rectangle is 1. I'm not writing it. So it will be f of 1 will be the area of the first rectangle. Similarly, f of 2 will be the area of the second rectangle. F of 3 will be the area of the third rectangle, and f of 4 is the area of the fourth rectangle. And I have to multiply it with delta, but delta here is 1. So this is 1, right? So multiplying with 1 doesn't change anything. So this will be the left Riemann sum. Whereas right Riemann sum, what will happen to the right Riemann sum? What point should I choose for the first rectangle, for the first interval? I have to
Two, sir.
choose 2 as my height.
Yes, sir.
Similarly, for the second rectangle, I have to choose 3. For the third rectangle, I have to choose 4. For the fourth rectangle, I have to choose 5. So for the first rectangle, you choose 2, compute f of 2 and construct a rectangle. This for the second rectangle, compute f of 3, and that will act as your height of the second rectangle. For f of 4, this will be there. For f of 5, this will be there. From the graph itself, you can see that the areas that I'm going to get, the Riemann sums that I'm going to get for left and right will be different, right? And also, if you compute also, you'll get different values. So for the right Riemann sum, it is f of 2 for the first rectangle, then f of 3, then f of 4, and then f of 5, right? So again, here every rectangle's length is again 1. So I'm not multiplying it with 1. Actually, it should get multiplied with 1, right? So this will be the right Riemann sum. What happens to the mid Riemann sum?
We have to take the height as 1.5 first.
Correct. So for the first rectangle, firstly you have to find the midpoints. So the midpoints are 1.5, 2.5, 3.5, and 4.5. Right. So once you have the midpoints, now what you have to do? You have to compute f of 1.5 and construct a rectangle like this. F of 2.5, construct a rectangle like this. F of 3.5, construct a rectangle like this. F of 4.5, construct a rectangle like this. Okay. So now when you compute the areas of each and every rectangle, you will get the first rectangle's area will be f of 1.5 plus the second rectangle's area is f of 2.5 plus f of 3.5 plus f of 4.5. Here you can see that the mid Riemann sum, the right Riemann sum, and the left Riemann sum values are different, right? And it may be true for most of the cases. For some cases, it may be equal, but for most of the cases, you will see that the left Riemann sum and the right Riemann sum and the mid Riemann sum will be different because the way in which you choose CKs are different in each of the cases. Okay. So now you can observe that this point affects the way you choose CK affects the area. Okay. So you should carefully choose CKs. So if you ask me, CK can be random. It can be any point. Okay. But for special cases, these are the 3 special points which we can choose for CKs. And mostly for problem point of view, we will choose these special points only. We will either ask you to compute left Riemann sum or right Riemann sum or mid Riemann sum. But one thing is, if you divide this into n equal parts and you tend n to infinite, all these 3 sums will come and converge to the exact area. Okay. So even the left Riemann sum, right Riemann sum, and mid Riemann sum may be different from for n is equals to 4. may be different for n is equals to 10, may be different for even n is equals to 100. But as you tend n to infinite, okay, as n grows, this area, okay, this area will slowly start converging to the same point, and which is the area of the rectangle. So, sorry, area under the curve. Okay, so that you have to be careful. Okay, any doubts
No, sir.
in Riemann sums? So most of us, even me, when I hear about Riemann sum, I think that it's a very complicated thing to understand, and how to choose the CKs, X1s, how should I divide n subintervals, and how should I tend n to infinite. So everything will happen at the same place, right? So we might get confused. But if you follow these 3 steps carefully, so after this session, you just go through the slides again, once again. So step 1, step 2, step 3, and finally step 4. Then it will be easier. Okay. So if you tend to forget what is happening here, then at least get the sense of how these steps are being done. Then you can easily compute the Riemann sums. Okay. So now the next thing, the last 15 minutes, I would like to spend on this definite integral. So what exactly this definite integral is? Definite integrals are the integrals with limits given to it. Okay. So as I was saying, as n tends to infinite, this will give me the exact area under the curve f of x from x is equals to a to x is equals to b, right? So this is how it is. And this is what is defined as, I have to put this. So the delta on top of it is like definition. So this is defined to be the integral from a to b f of x dx. So you see this integral is like, if I write s and stretch s from top and bottom, you'll get this kind of shape, right? So it is like that. So it is continuous summation in some sense. So integral is nothing but continuously you are summing up the area. So f of x is the height of the rectangle, dx is the length of the rectangle. Okay, so dx is very, 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 very small. Okay, and what you are doing, you are computing the area, and you are going to add these areas continuously. So adding these areas continuously is what integral is. That's it. So this limit n tends to infinite r n x f of f comma a comma b is nothing but you are considering infinite rectangles, right? So in some sense, that is what this integral represents. So this integral a to b is like you are continuously summing up starting from a to b, right? So that is like this. So you are adding up all the function values from starting to ending, which will give you the area, right? So this is what it is. Okay, it's like you are adding up straight lines to get the whole area. So all the straight lines, how many straight lines should I add? Infinitely many straight lines, because straight line has 0 area. And here R has some area, some finite area, right? So you have to add infinite areas like this, infinite values like this to get the exact area. So that is what integral a to b f of x dx does. Okay, and it is defined to be the limiting value of the Riemann sums. Okay, so I hope that is clear. And there are properties of definite integrals, right? So if you have two functions f1 of x and f2 of x and summation of it, and if you are computing the integral from a to b, the sum of two functions can be written as the integrals computed individually and summing up. Okay, so this is like the first property. And second one, you have c times fx inside the integral. You can pull out that c out of the integral and just compute this integral, and you just multiply c to it. Okay, so that is the second property. So whatever is independent of x, so this you would have studied in your class 11, class 12, right? So if it is independent of x, you pull out from the integral. So why we have to pull out from the integral? It's like even in graphical leaf, you see, if this is f of x, if c is 2, you'll have this, right? Now, if you are interested to compute the integral from a to b like this, you see the area that you compute under this black curve is just the twice of, right? So this area and this area will be more or will be equal, right? So you do 2 times of f of x, or you do 2 times into integral a to b f of x. Both are same. Sorry, it will not have the same shape. Why did I draw like that? So twice of it will be more than that, right? So this value twice, if it is this, then this value twice will be here, no? Right? So if the value is smaller, the twice will also be smaller. So it will have very nice, more waviness. It will not have the same kind of waviness, but it will have more waviness. And what does this integral say is, you compute this area, blue area, and twice it is same as you compute the whole region. You compute this whole region. Why? Because again, you do it with Riemann sums. This integral is nothing but limiting value of this. And instead of f of x, you will take c times f of x. You pull out c out. And then it will just become the Riemann sum of f of x. Right? So that way this is proven. Okay, so let's not get into the proofs because of the time constraint, but you have to understand everything using the Riemann sums. Okay, so then these properties make sense actually. So why we have to pull out c randomly, right? So that will come from the Riemann sums. And then the next thing is you can actually split the integral, definite integral. So if you are computing from a to b f of x dx, you can actually do it from a to d, some point between a and b, and then you compute from d to b. That will also be the same. And this is very easy to observe from the graph itself. So you have f of x like this, and let's say this is a and this is b. Okay, so this definite integral is nothing but the area under the curve, right? So this left hand side a to b f of x is this whole thing. And if you choose some point d, okay, and what you are doing is you are splitting this whole region into two regions now, and you are saying that you compute this definite integral, which is this area, and you are going to compute this definite integral and then adding up. So if you do this plus this will give you the whole region, right? So therefore property 3 also makes sense. So you can split the integral. Again, property 4 is like you have two functions where one function is always lesser than the other in the interval AB. The definite integral value will also be lesser than or equals to. Right? Again, this also makes trivial sense, right? So from graph itself. So you have f of x like this. You have some g of x like this, where your g of x is always greater than f of x in this interval AB. Okay. And you can see area under the curve g of x. So this is g of x. And this is f of x. So you can clearly see that area under the curve f of x is this much only. And area under the curve g of x actually contains this. Along with this, it also contains this, which is more than f of x, right? Therefore, property 4 also makes sense, right? So these are some properties of definite integral. Okay, and then comes even odd. Okay, so if your function satisfies much more properties apart from being just a function. If your function is an even function, what is even function? When f of x is equals to f of minus x, which is symmetric around y-axis, something like this. On the right side, you see. So this function is an even function because whatever is there, the shape on the right side of y-axis will just be the inversion of or the reflection you see on the left of y-axis. So if this is a mirror, they will just act as mirror images to each other. Okay, so such a functions are called even functions. And what is the use? If you have an even function and if you are trying to compute the integral from a to b f of x dx, then that integral, definite integral, is equal to, you take this b, negate it, minus b, you take this a, negate it, minus a, f of x dx. So graphically also, if you see, if this is AB and in that interval you are computing this area, right? So this is the integral AB f of x dx. If you see, since this is even function, even if I take minus b and minus a, it will also have the same area because of the symmetriness, right? So this property holds true for even function. Now, if I am trying to compute the integral from minus a to plus a, something like minus a to plus a. Okay, so this integral I am computing. So this region. Okay, so if it is even function, what I can do is I can use this split property. I can split it from minus a to 0 f of x dx, from 0 to a f of x dx. And then these two areas are equal because you see from the first property, you can say that these two areas are equal. So therefore I can write twice of, just compute 0 to a f of x dx. So you compute this area and take twice of it will give you the whole area, right? And this will only be true for even. When f of x is even, only then you can replace this with this form. Okay. What if f of x is odd function? So what is odd function? ECG. Yeah. Okay. It's not always ECG. Okay. So you should not see it like ECG. Okay. So f of x is odd function. What is odd function? F of minus x should be equals to minus f of x. Kind of pattern you can say. So something like this, it is symmetric around origin, right? So if you have right side, if you have like this, the left side is you do the reflection of this along y-axis and then do reflection along x-axis. So you have to do two things. So if you do that, then you will have this kind of shape. And this is an odd function, right? If you have an odd function, the properties are really interesting. So what will happen is, so the integral a to b f of x dx will be minus of integral minus b minus a f of x dx. And then if you're trying to compute integral minus a to plus a f of x dx, it will just simply be 0. Because whatever the area you have on the left side will be the minus of the area that you have on the right side. Because this will be in the downside and that will be on the upside. Okay. So this property is really interesting and it will help you in solving problems. Right? So something like this. So if you have the first example, if you see, you are asked to compute minus 3 to 3 x cube plus x power 5
Excuse me, sir.
dx. Yeah.
Sir, will you please a little bit slide? Yeah, just one line. Okay, sir.
Why?
Sir, I am writing, sir.
Okay, so you just take a screenshot, no? Why to write? So the same thing, no?
Yes, sir.
Okay. So you see this integral. This integral at the first glance might look scary. Might. It may not be that scary, but it might look scary. But if you see the inside x cube plus x power 5, what is it? Is it an even function or an odd function? So what is x cube
Odd function.
plus x power 5? Is an
Odd function, sir.
odd function. Very good. Because it satisfies If you see f of minus x, you will get minus x cube minus x power 5, which is minus f of x, which is minus x cube minus x power 5. Right. So this is an odd function and we are trying to find compute from minus 3 to plus 3. What will be the value? So you are integrating from minus 3 to plus 3. You are
0.
integrating from minus a to plus a, f of x dx, where f of x is an odd function.
0.
Right away 0. Right. What about this integral? This integral also, when there is mod comes in, mod may look very easy, but it can makes our life very difficult. But if you see this, you can actually split this integral, right? So you treat x cube as one function and mod x as another function. Now you see x cube is an odd function, right? So this is an odd function. This integral will go to 0, right? So always this integral is, this property is really helpful for us, at least in solving problems. Okay, so this will go to 0. What will happen to this integral? What is mod x? Is mod x an even function?
Yes, sir, even function.
Mod x is an even function. So what can I do to this integral? This integral I can write it as 2 times integral 0 to 2 mod x dx. So in the interval 0 to 2, mod x behaves like
Positive.
x, right?
Yes,
Yeah,
sir, positive.
positive, and it will simply be x. So I can just integrate. Now I can do the integral. So integral 0 to 2 x dx. I know how to do it, right? If I know the fundamental theorem of calculus, which we do in the next session. But this whole expression is now down to 2 times integral 0 to 2 x dx, right? If you see x is like this, a straight line, and you know how to compute this integral. So 0 to 2, right? It just forms a triangle, and you know how to compute the triangle's area, right? So this is 2, this is 2, so the area will be half into 2 into 2, so this will be 2, so this region will be 2, so that means this definite integral value is 2. So overall value will be 2 times 2, which is 4. Okay. So in that way, we can compute the integrals even if we don't know any formulas. Okay. So with that, I think I have extended a bit. So we'll end the session here. So after this session, I want you guys to just go back and look at what all we discussed and go back and look at the video lectures related to this so that you will get much more clarity and idea of this definite integral and Riemann sums. Okay. All right. So with that, we will end the session here. Thanks all for joining and have a great day.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Thanks.
Hello, sir.
Yes.